All right, hello everybody. Today we are going to continue with our topic of statics with probably the first time we're really going to talk about what statics actually means. If I had to come up with a definition of statics, in essence, what it is an analysis of systems at rest. And what rest means is that, let's draw a little diagram here. Statics means your objects are at rest, and if it's at rest, this is the key to all of statics. It means that you have to have equilibrium, otherwise known as balanced forces. Newton's second law. So if that's true, then I know that my sum of the forces, which we talked about, if we add up all our forces, we call that a resultant force. In statics, it means your resultant force will be equal to 0. Breaking that into component form, I can add up all of my forces, all my x component of the forces, that has to be equal to 0, and my y components must be equal to 0. And that's statics. I mean, that's really two of the three equations in statics for 2D analysis anyways. So we'll spend a lot of time with those two equations, and they aren't too bad because everything's equal to 0. Before we start working on some problems or what this means, we're going to have to define a free body diagram. So a free body diagram is basically a representation of an object with all the forces acting on it. Or written out, representation or representing an object with as a point or a box and showing all the forces acting on it. So for instance, if I had some stick figure guy here, oh, horrible start to that. Let's just make it nice and easy. And this stick figure is going to be holding up some kind of weight. Ooh, his arms are unusually long. And let's say that this person's holding up a 10-pound force. And let's say that there's some kind of wind pushing on this guy holding up the 10-pound force, and this wind force is going to be 5 pounds. And I wanted to draw a free body diagram of the situation that was going on. I could represent him or her just as a point, and then I'd have a series of forces. I know that there's a force pushing down that's equal to the 10-pound weight. It could be the self-weight of the person too. But neglecting that, there would be a force pushing up, which you probably learned from physics is called the normal force, or normal to the surface. We have 5 pounds pushing forward. Now in the study of statics, we can't have an unbalanced force. There has to be something pushing the other way. If the person is not sliding on the ground, there would probably be some kind of force of friction that's keeping him or her solidly placed. So that's what the free body diagram would look like, just representing the problem situation as a dot or a box, putting all the forces on there. So let's look at some easy examples before we get into a real life problem. If I have a 10 Newton force pushing one way and some kind of vector pointing the other way, and we were to look at our equation, sum of the forces in the x direction equals 0. We have to designate which way is positive, and we're going to use the normal positive to the right annotation. So I have a positive A minus this 10 is equal to 0, or A is equal to 10 newtons. Starting off easy. Moving it up a level, let's say that we had this same vector A, but instead of the 10 Newton acting in this opposite A, it's going to be at an angle of 20 degrees from the horizontal. So this is 20 degrees. Now, to be in equilibrium, I can see that this 10 Newton force is not only pulling to the left, but it's also pulling down. So I would need some other force to resist that. So we're going to add another vector up here. We're going to call it vector B. And this is what you would see, when we talk about rectangular coordinates or something like that. For this 10 Newton force, from our trig functions, I know that there has to be some kind of x and y component. So knowing that this is 20 degrees, of course, my x would be 10 times the cosine of 20, technically negative because it is going in the negative direction, and 10 times this sine. of 20 for my vertical. So in this case, if I want to know what vector A and vector B are, I could use sum of the forces in the x direction equals 0. Once again, to the right is positive. I have A in the positive direction minus the component in the x direction, 10 times the cosine of 20 is equal to 0. And that gives me a magnitude of vector A that's equal to 9.4 newtons. Same idea with the y direction. So sum of the forces in the y direction equals 0. We're going to have up as being positive. And if we do that, I have vector B in the positive direction minus this 10 times sine of 20 is equal to 0. So vector B has a magnitude of 3.4 newtons. Once again, starting off nice and easy. As an alternative, and we touched on this last time, what you'll see a lot is you'll have a vector. Well, we're going to have almost the same scenario where I have vector A and vector B resisting some kind of 10 Newton force. But sometimes instead of the actual angle, what you'll be given is, where this vector is being applied or where it ends up, and you can map out what its proportion in the x and y direction are, and use Pythagorean to find the hypotenuse of that, or get a relationship between x, y, and the total distances, I suppose, right? So if this is the case, if we were to go back and say our sum of the forces in the x direction equals 0, I have A going in the positive minus this 10 in the x component would be 3/5 is equal to 0. So A would be equal to 6 newtons. And same idea with the y direction. Like I said, starting off fairly easy here, at least I think so. B going up minus the 10, the y component of that 10 Newton force is 4/5 is equal to 0. I'm getting a little sloppy with my units because this is just simple, chug it out type of stuff. But in the end, I still know that I haven't changed my units, so I'm still in newtons. All right, let's look at one real example on how we would use this type of thing. Let's say that attached to the wall are two cables. One cable is going to be coming off over here. Make these cables nice and fat so we can really see them, right? The other cable's over here. And on those two cables, I'm going to be providing a force of 660 newtons. And what I'm going to be given is this distance from the center line up to the top cable location is 3 meters, and down to the bottom is 1.4 meters. And we'll also be given that the horizontal length of these cables is 2.25 meters. So from that, you could use Pythagorean, find out the length of each cable. I have 3.75 meters for the upper cable, and the length of the lower cable is 2.65 meters. I want to do that so I can break those cables into their components. So we can talk about these. I need to label them. So I'll label the top connection point as A, bottom connection point is B. The point where the vector is being applied we'll call C. So in this case, I have two unknowns. I don't know the tension in cable AC, and I don't know the tension in cable BC, but I also have two equations, sum of the forces X and sum of the forces Y equals 0. You're looking at the free body diagram. I'm pulling forward with a magnitude of 660 newtons, and I have these two vectors, two forces that are being applied on these cables. I have cable BC and cable AC. So let's call them BC and AC. You could call them TAC for tension in AC, or FAC for the force in AC. However, I'm just going to leave it as generic AC and BC for now. So what we're going to do, just like with the rectangular components before, we're going to resolve those vectors into X and Y directions and then add up our components. So if I were to think about what the new free body diagram would look like to give me a visual representation, what this is saying is I still have the 660 Newton force going this way, and then I would have the X component of both cables, so ACX and BCX added together, and in the Y direction I have this ACY, BCY. So we like working in the vertical and horizontal component system, so it makes the math much easier once I get there, right? Like I said, I have two unknowns, AC and BC. I have two equations. So let's start with some of the forces in the y direction equals 0. If I do that, I have this ACY going up minus BCY going down, and together that has to equal 0. So for my y component of AC, I'm going back up to my original picture, and I'm saying, well, I'm going vertically 3 meters over this hypotenuse of 3.75. So I have 3 over 3.75. You could actually calculate the angles and use sines and cosines, but much more work. And I'm moving the BC to the other side, just doing some algebra. And same idea, the y component is 1.4 for BC, the hypotenuse 2.65. What that gives me is a relationship between AC and BC. What I find out, that is BC is equal to 1.51 times AC. Go on and say sum of the forces in the x direction equals 0. So in the x direction, I have this 660 newtons in the positive direction minus my ACX minus my BCX. And I'm going to set the whole thing equal to 0. So I have 660 newtons minus AC, and then for the x component, now I'm looking at this, how far I go in the x over the hypotenuse for each one of those. So for AC, I have 2.25 over 3.75 minus BC times 2.25 over 2.65 is equal to 0. And here's where I'm going to take in this fact. I know a relationship between AC and BC, so I'm just going to plug that right in there and end up with something like 660 newtons minus AC times 0.6 minus 1.51 AC. I'm showing a little more work than I probably would normally, but it's good for you, right? Times 0.849 is equal to 0. So solve for AC, and I end up with the tension in cable AC is 350 newtons. And I can plug that back into that first BC and AC relationship to find out that BC is equal to 530 newtons. So two equations, two unknowns. I can solve them somewhat simultaneously and get my solution. A lot of these problems work like that. Sometimes you can solve for just X or just Y, depending on your individual situation. Hope that was helpful, and I will talk to you all soon. Thanks.